Okay, today is a big day in calculus world. I've been teasing you with this for the entire chapter. We've been dancing around the idea of what is an antiderivative, what is an integral. We've kind of shown how they're sort of related to each other. We've done a lot of estimating, right, where we've estimated what is the integral, or we found the area because a graph happens to be like a geometric shape. But we have not actually talked about how do you actually solve an integral, right? How do you evaluate it? If I just hand you an equation for a function, how do you evaluate an integral? So that's what the second half of the fundamental theorem of calculus does for you. And I want to remind you about this example that we did a few days ago when we first kind of discovered this connection, right? We took the function 2x and we integrated it, and we made a new function out of that. We said, okay, the f of x function is the integral from 0 to x of this guy. And then we figured out all these values, we drew the triangles, we found the areas, and we said, hey, wait a minute, this is really just the x squared function. So we learned that this 2x, because that's what the g of x function really is really just the same as x squared when you integrate it, okay? So if you were, for example, integrating from 0 to 3, right? If this was 3 and you were finding this area in here, what this is saying is you can just take the antiderivative, right? So the antiderivative of 2x is x squared, and you can plug the 3 into that, and 3 squared is equal to 9. Well, it happens to only work out quite that cleanly because I started you at 0, right? This integral was always starting at 0. Let's suppose for a second that I wanted you to integrate from 1 to 3 of the 2x function. Okay, well, what you would start by doing is you would start by taking this area, right? So that would be 3 squared, because we know this area that I have shaded here is 3 squared, which is 9. But then you would say, okay, well, here's the 1. I want to subtract this area, okay? And so I would say, well, let's subtract the area at 1, which we know is 1 squared. And that gives us 9 minus 1, so that gives us an area of 8. Okay, that's the area of this trapezoid right here. Now, if I felt like really being exciting, I would take the time to find the area of this trapezoid and prove to you that it really is 8. But what's more important to me is what we did here, okay? We took this 2x function, we did an antiderivative and got x squared, right? We knew that the antiderivative of 2x was x squared, and then I evaluated that function at the 2 endpoints, and I subtracted because I just wanted the area between those two numbers. That is the second half of the fundamental theorem of calculus. Okay, so this theorem right here, this kind of formula right here, if it's not written on your paper, it should be. So let's make sure to get it written down. This is saying to evaluate the integral from a to b of any function, you can take the antiderivative, which is what we've been talking about the last couple of days. We can take the antiderivative, evaluate it at the 2 endpoints, and subtract b minus a. Okay, so you're going to find f of b minus f of a. That's how we evaluate integrals, is by finding antiderivatives, plugging the numbers in, and subtracting to find the area. Okay, we are going to do this entire set of examples without a calculator, because you definitely will have to be able to do these without a calculator. There's going to be some mental math. There's going to be some fraction stuff going on. You'll get good at these, but they can sometimes be a little bit like cumbersome in just crunching the numbers, okay? But again, what you're focused on today is the concept, like the process. What are we doing here? So we are going to start with an antiderivative of x cubed plus x. If you want, feel free to pause the video, try to come up with the antiderivative on your own. X to the third would become 1/4 x to the 4th. That plus x, we know it's going to become an x squared, and then when I divide by it, I get a 1/2 x squared. Now, we've made a really big deal about the plus c, so I'm going to put the plus c down here for a minute, and then I want to show you something that happens with the plus c when we do this next step. Now what we want to say is we're going to take this antiderivative that we just found and we're going to evaluate it between 0 and 4. So this is the proper notation for this. You're going to want to get good at this. Okay, so now what I'm doing is plugging the 4 in for the x's. I guess let's just start with that. So notice my use of parentheses here. I find that usually is pretty helpful. 1/4 times 4 to the 4th plus 1/2 times 4 squared plus c minus, now I'm a little short on space on this one, but something really nice happens with the 0. And this doesn't always happen with zeros, but it happens a lot with polynomials. If I were to plug 0 in for this x and 0 in for this x, this whole first part would just be one big fat 0, right? And so the whole thing boils down to just 0 plus c. Those zeros are really nice when they happen because you don't have to do much math over here. What I do want you to see, though, see what I did there, is what happens with the c's, right? You have a plus c here minus a plus c here. That's going to happen in every single one of these problems. And so when you're doing this definite integral process where you're actually plugging numbers in, we actually don't really care about this, the plus c, because it's going to cancel itself out. Okay. So now our goal is just to evaluate this piece right here. Okay. Like I said, mental math time. 4 to the 4th, that's pretty big to do off the top of your head. But then notice I'm going to divide it by 4. So really what I'm doing is losing a 4. Okay. And so if I know 4 to the 3rd power, which is 64, I should be okay there. Okay. Did you follow me there? So 4 to the 4th would be 4 4s, but then I'm dividing by a 4, so I cancel 1 out. And so I'd be left with 4 to the 3rd, which is 64. Plus, this is 1/2 times 16, which is 8. And so I would give my final answer here as 72. That's my area under this function between x equals 0, x equals 4. Okay, next one. Start with an antiderivative. I see a 2x there. So the first thing I'm going to write down in my antiderivative is a 1/2. And then the antiderivative of e to the 2x is just e to the 2x. And so again, I put the plus c up here so I could make this point, right? But really, we don't need the plus c when we're going to be plugging in endpoints because we know it's just going to cancel out anyway. So then this is just going from 5 to 10. And then we just have to plug in the 5, plug in the 10. Don't be scared of the e's. We can leave things in terms of e. So I can say this is 1/2 e to the 20th power minus 1/2 e to the 10th power. There's really not much else I can do with that one. I'm going to leave it in terms of e, especially because I'm without a calculator. That one's good to go. I do want to point out that you could also see this written, and I'm fine with either answer, but I'm always thinking about those multiple choice questions. We could put the 1/2 out in front. Like that. Either one of those answers would be correct. Okay, now would be an excellent time to pause the video and see if you can get at least the next one on your own. Antiderivative. 9 would become 9 over 2 x squared. So I added 1 to the power. No, I'm so sorry. It's very late. I thought that had an x on it. It does not. The 9 just becomes a 9x. Okay. X squared becomes a 1/3 x cubed. And we are doing that from 0 to 3. When you have these zeros, a lot of the time you're going to end up with just a big 0 at the end, which is nice, right? Because there's less math to do. I don't want you to get too comfortable with that. If we had a 0 in this one with the e to the 0 power is not 0. So you do have to be careful sometimes with the zeros. But with these polynomial ones where you're just using the power rule, those zeros are going to cancel a lot of things out. Okay. So now let's plug in the 3. and I'm going to get 9 times 3 is 27, minus, okay, 3 to the third power is 27, but then I'm dividing by 3, so that makes a 9. Okay, minus, parentheses, this would just be 0 minus 0, so one big 0. And so I'm really just doing 27 minus 9, which is 18. Okay, got you all worked up for all the like hard mental math we were going to do, and then these have been pretty tame so far, but okay. Well, I might bite my tongue on that one with this next one because we've got some trig to do. So antiderivative of secant squared is tangent, and we are taking that from negative pi over 6 to positive pi over 6. Okay, you would be well within your rights to write this answer like this. Tan of pi over 6 minus tan of negative pi over 6. And then walk away and don't do anything else with that. That answer is valid. Once you've plugged the numbers in, you're good. But this type of thing will almost definitely show up in the multiple choice section. Okay, we can't run away from the trig forever. So let's go ahead and try to evaluate it so that we can refresh ourselves on our trig values. Okay, pi over 6 is here. Okay, the tangent at this angle, and I mean, we could go through and do like sine divided by cosine. When I taught you these, I taught you to just memorize them. So hopefully this rings a bell. But the tangent here is square root of 3 over 3. Okay, that's at pi over 6. Now, negative pi over 6 is down here. And this tangent is the same as that tangent, except this one's going to be negative because the sine values are negative. So this is a negative square root of 3 over 3. And so then if I had to actually evaluate this, I would say this is square root of 3 over 3 minus negative square root of 3 over 3. Well, minus a negative is really a plus. So all in all, this becomes 2 square root of 3 over 3 as a final answer. Okay, one more example here. Got some word problems here on this next page, but really for today, you're just going to be practicing a lot of this kind of thing, where you're just taking antiderivatives and then plugging numbers into them. Okay, but our old friend the table is back. Whenever I hand you one of these tables, the first thing I would look at is what is in the table. This is W of t. It didn't give us any context here, so I have no idea what W and t represent. Okay, but it says calculate the integral from 0 to 6 of W prime of t. Okay, that wording is super tricky here. Because if this was just regular W, or if this was W prime, if these two things matched, we couldn't really calculate, but we could approximate using a Riemann sum, right? Because I don't have an entire function here, okay? But I could approximate it with a Riemann sum. But these two things do not match. This is W prime and this is W. So let's think about what we just learned. We learned that to evaluate an integral, no matter what is in here, we need an antiderivative, right? So what's the antiderivative of W prime? Well, if it was W prime and you reverse the derivative, you would be looking at just W from 0 to 6. Well, that's just W of 6 minus W of 0. And conveniently, those numbers are in the table for you. Now, this is a great example of a place where a 0 does not just automatically equal a 0, because W of 6 is 12. W of 0 is 17. And so this gives us negative 5. Okay, let's talk about what we just found and how like this notation was way more complicated than it needed to be. When you integrate a function, what you're finding is the overall change, not the rate of change, but you're talking about how much did something increase or decrease in total over that period of time. So when I ask for this integral of w prime, I am saying, how did w change from x equals 0 to x equals 6? So if you think about what we did 12 minus 17, which is really just saying we shrunk by 5. From 17 down to 12, we shrunk by 5. That's our overall change in the w function. Okay, that's what an integral tells us. So don't get fooled by like the fancy, symbols and all of that. These questions are really not that hard. Again, anytime I see calculate an integral, my brain is saying I need an antiderivative. Antiderivative of w prime is w. This one's going to work just like the last one. Just be careful of the order here. This starts at 9 and ends at 3. So that means I need w of 3 minus w of 9, which is 4 minus 9. Well, that's convenient. Also negative 5. Now, you might be looking at this and saying, well, this increased by 5, right? But this is having us walk the other way. So this is just saying, if I start down here and move to where x equals 3, what happened to the overall value of my function? It shrunk by 5. Okay, so super easy example there once you can kind of sort out what all the notation is telling you. But this is going to be a really, really important thing for you to get good at. So take your time on the homework tonight with those fundamental theorem examples. You're going to get really good at antiderivatives. You're going to get really good at mental math. I'd like you to do as much as you can by hand. And then tomorrow we'll talk about how to do some of this on the calculator. Okay, that's it for me. Have a great night.